It's gonna work.
Yep.
Yay. Okay. So I'll wait for the confirmation on my end and then we'll roll in.
As everyone starts piling in.
Yeah. We'll see who's here. Okay. All right. So we are officially live. Yay. So welcome in everybody. We have a very, very special guest today, Dr. Scott McIntosh. He's a he used to, well actually well, let me just read what we have here.
Oh
Um
no.
Yeah. Was the deputy director of the National Center for Atmospheric Research, NCAR, in Boulder, Colorado, and spent 25 years of experience in solar and astrophysical research. Scott presently serves on the White House Office of Science and Technology Policy, Space Weather Group, and is a lead of its research sector, and is a chair of the American Meteorological Society Scientific and Technological Activities Commission for Space Weather. It's a quite a resume there. But if you want to talk about the
Sure.
linker space, because that's a fairly recent thing, feel free.
Yeah. Maybe get there at some point.
Yeah. But we're very happy and thrilled to have him here because we're big fans of his work. Um, always especially with the solar cycle stuff. So hey, so I'll hand it over to you.
Oh wow. Okay. All right. Well, it's a real pleasure to be here chatting with you. And whoever's the assorted masses out there. So um let's see if I can get this thing to work. New laptop is always a bit finicky. There you go. I can see you. Can you see
I
this?
can see the slides.
All right. Okay.
Looks
So
good.
my boss really loves this picture and like in many ways. And I might get into that at some point. It's pretty epic. You'll see it appearing all over the place in our materials because, well, here's a hint, spot North Korea. So anyway, so everybody goes to scowling at the screen to look at North Korea. All right, so
It's
real pleasure to meet you guys. I'm going to talk about the present solar cycle and I'll go back a little bit in a flashback to look at things that we've done in the past that kind of led us to this point, and then give you a little bit of an update, and then maybe something else. All right. So as I said, there's some untested material at the end of this, so I may have to shoot everyone that watches it. So
oh no.
all right,
Hide your
but
eyes.
Yeah.
yeah. So brain bleach. Get your bucket of brain bleach ready.
Yeah, let's do
Um.
this.
So the other point I want to make is that, unlike the media over the last couple of weeks that would lead you to believe that at 12:05 Pacific Daylight Time last week was solar maximum last Wednesday,
Right, yes.
it's more than just a point in time, right? So I know I'm probably preaching to the choir at some level, but we'll get to that in due course as well. So anyway, so here we go. Why the hell do we study solar activity? Why is it important? Why do we forecast it? Propaganda slide, courtesy of my friends at Swipsy. There's a lot that we do in our world in the last 50 or 60 years that depends on spaceborne technology. Even our ground-based technologies are important, are critical to space weather. So we study it to try and protect these assets, right? So, and this is just the light stuff, not even the dark stuff. The dark stuff, I think, dwarfs the light stuff. Talking about dark and light, we'll get to that a bit later on too, but that really provides the motivation for what I started doing all of 10 weeks ago. So, I'm a 10-week-old baby at some level, so just bear with me. But the
All
other reason we do this is because we live in the atmosphere of our star, right? And there's an old Michael Caine line that not a lot of people know that. If you've seen a share of Michael Caine movies, you would know that line. But we live in the atmosphere of our star, and so its tempestuous behavior jacks with us all the time, right? And so, we live in a stream of particles and light. The light keeps the planet's weather going. Don't believe the hype. The particles do all kinds of weird things, including creating beautiful lights in the sky, right? But as I always tell the kindergartners, when you get the beautiful lights in the sky, it also means that someone's spacecraft might be flying up there. So anyway, it's all good. The part of the reason we study this stuff is also because of just intellectual curiosity. Since folk have been observing the sun since 1600 through telescopes, a pattern's kind of emerged, right? So there's several patterns. This one's probably the most poorly understood but most prominent one, is the fact that the sun has an 11-ish year cycle. Ish should be in italics and bold font, or Comic Sans, whatever you prefer. But, understanding the variability of the star is challenging, and to do it from really a miserable data set like the sunspot record is even harder, because, of course, the sunspot record drops out on you at times between 1630-ish and 1700. And it's not because it wasn't observed. It was actually observed probably more at that point in time than any point since, because of the dearth of sunspots, these dark features on the sun, right? So I'm going to make a ton of assumptions, Chris, Mary Beth. So if I make an assumption that seems like a step too far, just pull the crook in and yank me out, ask a question, right? So
All right.
We'll do FAQs at the end too, or at least
good,
just general questions.
All right. So anyway, the other more obvious pattern is that when we started to look at the spatial distribution, so you jump forward, 150, 200 years, and you notice that this latitudinal progression of these dark features on the sun presented a pattern, and that's shown in the top plot here. So that's the infamous butterfly diagram. So if you rotate your head at 90 degrees, it's just easier for some of us to do than others. It creates a butterfly. And so people think that from just the information in the butterfly diagram and the total number of spots, you can forecast what the sun's going to do next. That's really bloody challenging. That's not a lot of data to constrain a huge physical problem, right? So you get 400 years of sunspot measurements, 100 years of magnetic field measurements, because it turns out that these features are also magnetic. I'm jumping through several intro slides here, and there's an infinity of potential solutions to the problem. My PhD thesis was on a thing called inverse problems. For those of you who don't know what inverse problems are, they're like mathematical tools where, and one of the big challenges is that if you've got really crap data, there's bajillions of answers fit the data. And the trick with inverse problems is being able to filter out all the crap and get to close to the real solution. So 400 years of data, 100 years of magnetic data, an infinity of potential solutions to the problem. Was an exaggeration. But for sunspot cycle 25, which is the question mark in this guy, there was something like, close to 100 potential forecasts submitted, right? So I think of things in a really kind of stupid elementary way, because I'm stupid in elementary. And so I think a lot about driving questions. And I also think in the context of Kraken a lot, because it's one of my favorite rums. So, if anyone's out there and wants to sponsor me, I'm totally up for that. I'll drink as much as you can throw in my direction. But the other thing is that I always think that there's some hidden Kraken underneath, and I want to take a snap at it. The Kraken in this case is a magnetic one. And so how does the sun's magnetic engine produce what we see? Can you observe it? Right? You can't directly observe it because it's obscured from view. And so how best can you do that? What techniques? It's like CAT scans, MRIs, other equivalent type of ideas for the sun. And then you make the bold leap and say, well, if I can understand that, observe it, characterize it, then can I forecast? Can I play it forward? One of the motivations here for linker space, and actually one of my driving motivations are, you'll see in things like the swag and all these other things, are what are the impacts of the varying activity in the near Earth environment on the ground, right? There's a motivation for doing it. The other motivation, of course, that's missing is that I like to tease people. So, with that being said, how do we think that the sun's magnetic machine works, right? So the kraken lurks below the surface, and we imply what it is through observing its tentacles. Here's an example of tentacles, right? So this is the magnetic field of the sun varying over 3 decades, 3.5 decades. It's an old movie now. You can tell that from the crappy resolution of the magnetograms they're going to play. But, the idea is still there. So remember what I said about butterfly diagrams and sunspot numbers. This is the third dimension of data. So now you ingest this magnetic information, its variability in space and time, and that is enough to constrain the model, right? Probably not. So you've got this massive internal machine that dictates the time and the location when these little magnetic features appear. That's the essence of the Kraken, right? Arbitrary World Cup image because I'm Scottish, play a lot of soccer. Over the last 3 decades, our community's been engaged in the ultimate pursuit. What comes next? Okay. Failed. Fail, fail, fail. Right. But failing in different ways and maybe getting progressively better. But it's kind of become the World Cup of solar and space weather science, except that nobody's won it. Right. So it gets to the quarterfinals and then the tournament gets scrapped. Right. Oh, and here's Mr. Logan again. So, in 2019, now a friend of mine, Sarah Scholes, wrote a cunning article on the last time the austere panel of experts met to develop a consensus of what cycle 25 was going to be. I put the QR code up here. If anyone's interested in reading it, I always look back at the alt metrics after I give one of these talks. And you can see the spikes in the readership. So Science Magazine probably owes me a fortune. So, but this idea matured from a paper in 2020. So we put out a forecast that was quite a radical compared to the consensus forecast, and you can compare the two here. We actually didn't have a timing estimate in it, so plopping it in the middle of 2025 is not a great thing. It should just be a blob, sitting at like 225, spanning across the way. The green curve here is the mean solar cycle over all time, so since 1750. And blue here is the so-called consensus forecast from my peers that came out of the panel. So we basically had something that was twice as big, and there was no way we believed that solar max was going to be in the middle of 2025. No way, it just was not going to happen. That's the part of the forecast that nobody really talks about or pays attention to. Like it's out significantly in time, right? So this is the state of the game. At this point in time, Houston does have a problem, right? You've got something so we're either barking mad, and that's absolutely acceptable, or someone else is barking mad. So anyway, now we're going to go back in the Wayback Machine. Okay. So we're going to travel in time. Pick your favorite sci-fi movie. I'm showing my age, I guess. Actually, wasn't it just Back to the Future Day the other day? But won't go back. So since I was a postdoc, since I was knee-high to an academic grasshopper, I've been working on spacecraft. And one of the spacecraft that I worked on was the Extreme Ultraviolet Imaging Telescope on SOHO. So it's one of the last remaining instruments functional on SOHO, which launched 6 weeks after I started my PhD, believe it or not. So it's as old as me. So and I was an instrument scientist, and my boss at the time said, there's these little these little bright features on the sun's corona. You should write a piece of code to identify them and then maybe track them. You might learn something, he said. Scoffing, I think. No, he wasn't scoffing. I think he actually knew what I was going to find. He just didn't know how long it was going to take me. So anyway, so you can see the picture on the left is a kind of quietish corona, 1,000,000 degrees. You can see that it's pockmarked with these little bright features. They're about 4 or 5 arc seconds across. And the right-hand side is what you get when you run my detection algorithm over it. So this thing's basically been running for 23 years. In 2011, 2012, I noticed something really freaking weird, right? I wouldn't call it quite the bathtub moment, but it was close. And so what we noticed, and that there was a few features. So this is actually from a PowerPoint slide that I gave to the then deputy director of NCAR, Maura Hagan, to show to the NSF, because I'd found this thing that was truly strange. I thought I'd find a correspondence between the timing of sunspot cycle, the timing of sunspot emergence and all these other things, just by tracking these tiny little stupid features on the disk, right? And so the picture of the tracking images at the bottom there, and I've, my what age was she at the time? 4 or 5, drew straight lines on it, right? So I got her, so like even a 4-year-old could draw straight lines on this. That was part of my shtick at the time. Um, and we'll get to that in a minute, because she drew the next set of lines that ended up being cycle 25, right? So I got in the middle of this, I had shingles twice, right? So I had shingles twice in the space of 8 months when I did this work. I analyzed about 20 terabytes of data in the space of a few months. And what we noticed was this patch in time between 2010 and 2012, there was a huge overlap in time, right? You could see that there's 4 things there at the equator, but the sun has no spots. Why the hell is that? I wasn't aware that, of course, that the smaller scale magnetic fields were following what looks like the butterfly diagram, right? So, I'm not going to get into it in a lot of detail, but the idea was that there's 4 bands going on here, and then I see these 2 weird episodes that have got the dashed vertical lines. I don't think my cursor's projecting here, but you can see one in 2011, and you can see another one in 1997. And I was like, this is really weird. Stuff just comes to an end at the equator, and then at mid-latitudes, boom, you get spots. That's really freaking weird, right? That shouldn't happen on a star. Things are really diffuse, right? Nothing that sudden happens on the inside of a star. But it seems to do it here. In fact, I've got 2 of them. That's really weird. Then I started getting really crazy, right? And I called my then 4 or 5-year-old in. Can't remember. I'll have to figure out what age she actually was. And I started to analyze a lot more data. And it turned out that, yeah, this was pretty robust, that there was an endpoint. There was a definitive end to this pattern of these small scale features. And right at that endpoint, new sunspots started to emerge en masse at mid latitudes. That's really, really weird, right? So my objective, why I started analyzing data, was I was actually trying to follow the wings of the butterfly back in time, right? So the butterfly wings are, and literally, like you said, they kind of, I can't even do a butterfly, whatever, right? They look like this. You get the actions going here. But I was trying to actually use the data to follow them back. So if this scale of magnetic field was there, were there other scales of magnetic field that were also there, right? So it's kind of like a forensics job. So I started doing that, and I found one. In fact, I found the one that was connected to these bright points, right? So, and what I noticed was that even when there's no bright points present, there's a scale. There's like almost like a convective scale of that size, about 100 megameters. So these little bright points are about 100 megameters apart. That's a whole other talk on its own. But what happens is, if you just track that scale, you start to get something interesting. So if you look at this image back in 2012, you can see at high latitudes, there's a hint of something there, right? We'll talk about that in a minute, but do you see those magenta lines? So
Yep.
there's magenta lines on these plots now. So you've got the continuation of the yellow ones in towards a meeting point, because I'm at this point guessing that there's going to be another conflagration sometime in 2020, right? But I'm also saying, well, based on the 20 terabytes of data I've looked, this thing repeats itself every 11 and a half years at 55 degrees latitude. You can ask a question, why the fuck is it 55 degrees latitude, right? Excuse my French. That's a great question, by the way, if anyone wants to ask it. But But I noticed that every 11 and a half years, this happened again and again and again and again. So I got my daughter to draw the same straight line starting at that point in time. Would we see the next cycle? And of course, the answer is yes, right? So you start to see these little tendrils, and this is all from a slide deck built. This is now a continuation, of course. So this is the original one. This is the version I came back to 5 years later because, like a true moron, I kept beating my head against the wall, and this is what we got, right? So at this point in time, we're speculating we'd see the first sunspots of cycle 25, kind of late 2019 into 2020, right? So we'll leave that there, right? So the question was, how are we doing? Well, it's great. And as STO launched, so back when I was a young whippersnapper, I was actually a T-boy for the science definition team for the Solar Dynamics Observatory, right? So I was the gopher when the science definition team was meeting. So I would interject all kinds of nonsense into those conversations, right? So but this is from the very start of the SDO mission. So this is one of the first images I made of the end of cycle 23 into cycle 24, just to get an idea of how abrupt that change was at the sun's equator. So it's so abrupt that over the timescale of one rotation, so 28 days, there's something there and then there's something not there, right? It really just shouldn't happen. So this is when we started saying, well, this is the end of some kind of cycle. We were starting to speculate that it was the underlying magnetic cycle. But, it was called a termination point at the end, and it eventually became, the terminator, right? So, because, well, I don't know, child of the same decade, I guess. And so we started to put more tails on this thing and started to track it longer. And 95% way through writing the paper, I found a paper that was in Nature in 1988 by a really bright guy called Wilson. So if anybody, and Wilson has a book, I usually carry it with me because it's like my Bible. If anybody wants to go read this, is a Nature paper called blah, 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 something the extended solar cycle from 1998. And they basically found the same thing 20 years before, right? But it just deep sixed, completely disappeared. I could not figure out why it only had 75 citations over 20 years, right? It was such a profound piece of work, and it was the culmination of four authors' work for a whole decade and a half before that, right? And then it just disappears. It's baffling. Still, I've interviewed the remaining members of that set personally, and like, tell me what happened. We'll get into that if you want, but it's a horrible story. So, yeah. So anyway, so what we basically found was that we were seeing that we were basically seeing the magnetic cycle. So it was the Hale cycle. It was always a thing when you learn solar physics is that, they've got the 11-year sunspot cycle and there's a 22-year magnetic activity cycle, but nobody ever goes into any detail at all about the magnetic cycle, ever. Just get glossed over because you can't observe it, right? You can only observe it through those crazy tentacle plots, right?
Right.
And so we had to kind of speculate. So here's where we were in 2020, right? So this is us starting to look at this problem. You can see the two termination events in here. We're desperately tracking the next one. We're like, when's it going to be? We're speculating on when it's going to be. Well, so you overlay the butterfly diagram on it, you go, fuck, that's good, right? And the problem is that you're not actually changing. You can't change any of this background. You can't change the clock. The clock is just going to do what it's going to do. And lo and behold, the data just falls on top of it, right? So either we're mad or something's going on. But what we were really waiting on was the first tendrils of cycle 25 popping up, and you can't quite see them in this plot. We animated this at the time, and that's at the left. And the interesting line on this one are the green dots, if you can see them. Those are actually the highest latitude filaments in the system. You know what a filament is? They follow the neutral lines in the field. They become prominences when you see them on the edge. And you can see that these trace where the magnetic field is identically zero. So you get this weird thing that goes off to the poles. I was like, that's really cool. It's just another one of these things that fits into the puzzle. But that's not new because my peers in 1998 also found this. So I was a wee bit defeated at the time. Because yeah, I just refound something that someone did the Hale cycle ago. And it seems like that's part of the deal. Here's a beautiful, I don't know, it's a butterfly diagram with the highest latitude filament and the sunspot number and terminators. And now you start to see, because we were accused of cherry picking the data with 1 or 2, but now we have 14, right? I think 14 we're getting out of the randomization statistics. And what you see here is when the really wild thing, remember how I said it? Within 28 days, there's something there, and then there's nothing there, and then you get spots. The really eye-opening thing about the filaments and the prominences was, look what happens at high latitudes at the Terminator event. So all of a sudden, this polar reversal process also happens. It doesn't just happen once. It happens 14 times, and it happens in both hemispheres. I was like, holy crap. I mean, literally, holy crap. I think I might have fallen off my chair, right? Because now you're talking about global scale connection. It's not you've not got this freak occurrence of you switch off at the equator, switch on at mid latitudes, and then nothing. You've got it going on at mid latitudes and high latitudes, and it's like that. Right? It's not taking years, it's not taking months, it happens. So we started exploring what was going on, right? So here's the kind of high level hypothesis, and I'm taking a lot of time to go through this. And you know that I've got 322 slides to get through. And so the hypothesis is that these magnetic Hale cycles interact and they overlap in space and time, and they interact with one another because magnetic fields interact, right? One of the big differences between what we are proposing and what's been proposed for the last 65 years is that in the contemporary models right now, the magnetic fields in the system are passive, right? They go along for the ride. They don't determine the ride, right? And so I think what we are seeing, or what we're saying at least, is the magnetic fields are at least equivalent to the circulation flows that are going on inside the sun, and in some cases dominant, right? Which is a completely different kind of physics. And that's really our underlying motivation of pushing the needle with the forecast, right? It was the sun presented us with an opportunity to poke the bear, right? And so we poked, right? Because we think that this is carrying some weight and an understanding of what our star does. Those magnetic cycles start regularly at high latitudes, almost identically at 55 degrees latitude. Again, that's a great question to ask. Their migration time to the equator is variable, but it averages out about, I think, 17 and a half years. Longitude in this problem is extremely important. The sun is not flat, right? It rotates. And so you get all these weird rotational things going on that are a lot of fun. The interaction is not always the same in these Hale cycle bands, and so you get a lot of randomness introduced. You get things, so they interact inside a hemisphere and across the equator. So you've got this large coupled system. If anyone did beyond high school physics, it's like having a coupled pendulum. Like you can get these weird patterns that show up. And the interaction of those bands shapes the evolution of sunspot cycles, including the amplitude. The amplitude was the first thing we were interested in, right? And so we speculated that the separation of these events was somehow a proxy of what was going to come next. I'll get into that in a wee second. I see there's a bunch of questions flying in. Do we want to deal with those now, or do you want to deal with moving on?
No, it's just me asking why 55 degrees?
Well, that's a great question. So, anyway, so because one's not enough, because three's not enough, because 14's not enough, let's go and get 24, right? And so we were challenged in the paper that we wrote on Terminators back in 2019. Well, I don't believe you. I think you're fucking with the data to make this happen, right? You need to come up with something algorithmic to verify your own analysis. It's like, okay, challenge accepted, right? And so we came up with this thing, and actually I give a lot of credit to my friend Sandra Chapman, who works on tokamak plasmas and looks at flaring and stabilization inside of tokamak plasmas and things like that. And she said, well, it's like your Apple Watch or whatever has a Hilbert transform running all the time trying to detect when your heart's going to explode, right? So Hilbert transforms are really interesting. Nobody should use Fourier transforms to analyze the sunspot cycle. Use Flash, right? Hilbert transforms deal with really well with non-stationary time series, and what that basically means is that the phase of the signal changes with time. So in a Fourier signal, it has constant phase, but in a Hilbert analysis, you can allow the phase to vary. So your sinusoids are never really sinusoidal, right? So anyway, so you get your sunspot number record on the top. We detrend it using a magic wand. That's a blue line. Once you remove that, you get the black curve in panel B, and then panels C and D are the amplitude functions. So the amplitude of your sinusoids vary with time, and also the phase. And what we found was that when we looked at the Hilbert transform phase function, it was actually a beautiful indicator of the terminator event. So what we're basically looking at is the highest amplitude, most rapid change of the time series, right? So like I remember I said how it just switches on. So that the Hilbert transform is just picking up on that. And so in this case, that's when the phase equals 0, right? So you can see our yellow dots are the ones that we cherry picked and cheated on. They were pretty much verified by the algorithm, which is great. But there's some other interesting features in this data set, right? So we started to poke around. Look back at 1800. Do you see the pattern? Right? So when the sunspot amplitude comes down low, the terminators get separated. And when you go up to when they become compressed is when you get high cycles. It's really weird. It's like a barcode, right? And we started to think about a relationship. So we've always been thinking about how these bands overlap and interact, and that somehow there was a measure of the upcoming cycle strength because it's all about how much one Hale cycle eats into the next one. The clock at high latitudes is always fixed, but there's variability in getting from high latitude to the equator, right? And so depending on how long it takes to the equator, it eats into this phase of the clock. I don't have a great schematic for it, but we'll get into it in a minute. So we did an experiment. This is now infamous. It's definitely not famous, right? So we said, well, we're going to measure the separation. We've got 24 of these things. We're going to look at the intermediate cycle strength, and then we're going to compare it to the upcoming cycle strength because we think really it's about this idea of one Hale cycle eating into the next one. Here's the two outputs. The intermediate maxima has 0 predictability, so it's not a good proxy because every answer works pretty much. You always get the average. Shock horror, right? But on the right-hand side, you start to see, oh my God, look at this thing, right? So it's like it's almost a linear relationship with the terminator separation and the next cycle strength. Okay, and so at this time in 2020, we're like, holy crap. We thought that the terminator was going to be, you saw the plots from early on. Sometime in 2020, we're going to have this terminator event, which means that this cycle is going to be really short, which means that the amplitude of the next one is going to be really high, right?
Right.
And so this is what you get, right? So this is the basis of our paper in 2020, I guess, and its alt metrics were off the frickin' charts, right? This was the highest read paper in all of astrophysics for 3 years, but not cited, right? Okay. Right, it's just
That's
crazy.
wild.
And so we get to this point. I haven't updated. There's your animation plane. So we've observed Hale cycles, or what we think are Hale cycles. We've now verified that, right? The data seems to support this idea that the Hale cycles interact to shape something, right? The key feature that we've seen right now is their death, right? So these terminator events, and it seems to be where that terminator event is relative to the clock, jacks with stuff, right? It shapes or at least modulates the amplitude of the next sunspot cycle. But the problem is that the picture of solar activity that this describes is not in the textbooks, right? So you've got this problem now where, like I said earlier, you've got all these fields that are being stirred around, but they're passive. That's what we have in the textbooks. But this picture would appear to indicate that the magnetic fields are actually jacking with one another at scale, right? So it's kind of like there's this process in the Earth's atmosphere called teleconnection, right? Where the weather systems in the two different inside and outside of the hemispheres know about one another because of gravity waves and things like that. Well, it may well be that the sun has the same problem, right? And so the magnetic fields inside the sun are really not passive. But it turns out that understanding these terminator events is actually pretty important. So anyway, back to our craziness. And so if those of you have been following us on Twitter or Facebook less, try to stay science off of Facebook these days. We were basically been testing a hypothesis in real time, right? So we've been poking the bear in real time, right? As fun as that is, it's sometimes a pain in the ass. So in 2019, we thought, all right, we're going to start broadcasting this. And of course, the question for me now is more, what are the what are the real world risks associated with adopting a ship model for solar activity?
Right.
If you're putting $1 billion into a fleet of spacecraft, what would you want to know? Would you want to know that pretty accurately or not? Just a smidge? Okay.
Just a little.
Okay, so our projections of a 2020 Terminator were wrong. Believe me, we have learned. We now know how. I think we know. I see Bob's on here. I think I know. We know how to time this, right? We'll do significantly better next time. We're 0 for 1, I guess. But this is the progression of our sunspot of our extreme ultraviolet bite points. You get a really good perception now of this overlap in time, right? So you're looking at the scales of 4, 5, 6 years back in time of the butterfly. I haven't overlaid the other scales. There's clearly 4 bands of things. Those bands of things come to a very abrupt end at the equator. Apologies if I'm beating the drum, but then you get this activity significantly increases at mid latitudes. There's all this crazy shit going on, right? So I'm back to my favorite animation again, right? So I'm just taking natural pauses to reiterate everything I just said, right? Hale cycles, the overlap of the Hale cycle sets sunspot amplitude. The problem is that our Terminator didn't happen in 2020. It didn't happen until December 13th of 2021, which meant that we have a Terminator almost right about the average, actually, 10.8 something years. Believe it or not, the average is like 11.001 or 2, right? So there's no numerology, right? It's just a fluke. Turns out before 1850 it's different, and then after 1850 it's 11. So there's 2 different averages. So
That's interesting.
but if you take them all, it's 11, practically speaking, right? But that means that if it's 11 years, then you'll get an average cycle out, which if you look at the numbers mentally, you can draw a line and say, yeah, I'm roughly in the average. There's the big M there for the mean, right? Now, the interesting point for you guys is, do you see the 24? The 24 sits right on the line, right? So if I'd done this exercise in 2011, I would have been able to predict the amplitude of cycle 24, and everyone would have said I was bonkers, right?
Right, right.
But it works pretty well, and it wasn't far off with 23 either, right? So it was within 1 sigma, which is pretty damn good. Considering, remember, I talked about the World Cup and nobody won the World Cup. In fact, the tournament was abandoned in the quarterfinals. So for those of you that are interested, one of the things that happens really beautifully when the Terminator happens, because the sun's magnetic field basically expands like an umbrella, the cosmic ray flux that bathes the Earth just drops like a freaking stone, right? It's such a beautiful diagnostic. Terminator said about Bob, start watching the cosmic ray flux. Okay, right? Drops like a stone. But who could have predicted that, right? The other thing that happens is that, like I said, is that the corona springs to life. So here's another beautiful example, right? So you look at the mid-corona of the solar atmosphere, there's a lot of decay at the equator. All of a sudden, the decay goes away. The mid-latitudes spring to life. The extreme ultraviolet lines double in brightness in the space of a rotation, right? Right? It just boom, just switches on. One of the interesting things is here that it's a function of temperature, right? So the bottom plot here shows that if you go from cooler lines, it's about a 5% change, and then right up about 1.5 million degrees, 2 million degrees, it's a factor of 1. So it doubles. So the brightness of the corona just doubles, right? It's bonkers, really crazy shit, right? But nobody's ever noticed this before. So, but all that meant is that we had to revise our forecast, right? And I don't think this is the revised one. This is the revised one. And so this is pretty current. And so our red thing here is our statistical model. I think I changed this today because I wanted to include cycle 20 in case someone wanted to ask a question. And you can see that stacked up against the data, it's actually doing pretty well, right? So this forecast was locked in early 2022. Hasn't changed.
Yeah,
And so what's that?
it's holding up pretty darn good.
Yeah, I guess we should have put some money on it, right?
Absolutely.
So not that we'd be wealthy because we'd be the only people betting probably. So but it's holding up pretty well. If I zoom in a little bit and we just look at the Soho era, because that's really my academic lifetime here. It's like my own heart rate here. It is doing pretty well. It's not getting every bump and wiggle. And last fall was really interesting because as you all know, the activity kind of just died off for a little while, but it's still doing significantly better than that blue curve. In fact, you now see that the maxima is properly adjusted to be where we said it would be in middle of 2024 and not a year from now, which was never going to happen. Maybe someone can ask Bob that later on. If I zoom in and look at it even further in more gory detail, it's horrible, but it's still doing pretty damn well, right? So, but so if you were using that blue curve to launch your fleet of 1,000 spacecraft, and you're using this thing to estimate the amount of drag, you'd be in deep shit,
Yeah, definitely.
right? So, anywho, how's it going? So this is a fun little animation. Um, I enjoy doing stuff like this. I'm not, he's back again. No, go get someone else to help you. Go.
It's all good.
Yeah, no, it pisses me off. So anyway, he'll watch this in 20 years' time and go, Dad's a dick. So here's an animation. So it's just basically taking 11 years of data around a Terminator and scanning through, right? You see it? And the bottom plot is just what's in the green window. So I've basically adjusted time. So I basically freeze time in the bottom panel. And the idea is just to build a statistical average. And look how beautiful that is once you average over what the 14 cycles that are there. So there's actually an average butterfly, right? If I plot the average butterfly against the contemporary data, wow, it's amazing. It looks just like it's doing what it should do, right? There's no magic, no mystery, nothing. It just turns out that it's the underlying cycle that may be the important one, right? If I look at the statistical average now and compare it to the monthly data, yeah, there's bumps and wiggles in there, but I'd say that's pretty damn good. We'll get back to the shape of this in a second, but you see those vertical dashed lines? This is a bit of work that maybe someone can ask Bob about later on, but we basically identified that the unit cycle could be divided up evenly into 5 bits, which is kind of amazing. And you can see, the vertical dashed line at 2024, probably January, February kind of time, is when the statistical model, if the terminator is going to be in 2032 and a bit, would put solar max in February of this year. So we can play with that a wee bit. But as it stands, this is where it's going. And you have, because this is actually set to an average cycle length, right? So we've got the Terminator in December of 2021, and then we go out 11 years for the next one, and that allows us to shape the statistical average. This is what you get. The data is comparing favorably to that. You can also do things like the solar radial flux from this, and guess what? It's doing pretty well. We didn't get that big spike, but I don't think anybody did. It was crazy, but it's going to help the mean, the 13-month running mean, right? So anyway, whatever. It's looking good. Here's a kind of more of an explanation on the time scale. So you've got your start and your end with your terminators, left and right. You've got turning it up to 11 at solar maximum at 0.2 of a cycle. This sounds crazy. The next bit that's exciting is what we thought, what comes before a terminator? Is it a Cameron? Is it a Kyle? What is it? Right? So, we've called it all kinds of things. I don't know if we call them Camerons. I think Bob will correct me, but we've not really got a solid. But I think now I just call it the activity cliff because it's when everything goes to shit, right? Just stops. And that will be the next huge test of this. And then, of course, at 0.8 of a cycle, you see identically solar minimum. So it's really weird. You get this, you can break up the statistical average into 5 different chunks. And each one of the chunks lands at an epoch. If you notice that at approximately actually 0, 0.6, and 1 all go through about 50. Right? So there's some symmetry in this. I don't know if that makes it beautiful or what, but there's some symmetry going on in some of the physics, but that also kind of gives you an insight into how you can project forward, right? So as you go through these landmarks, that allows you to play with time a little bit. Anyway, and of course, then I've got the question mark, right? So there's one I've not labeled. It's just a big orange question mark.
I like it as a question mark.
Yeah, well, we'll get to that question mark in a second because that's right where we're at right now, right? So, there's more to this puzzle, and forgive me for using this trope, right? So there's a light side and a dark side to activity. The ascending phase I always call the light side, but I always love to refer to the dark side of the cycle, and that's because it's all coronal hole dominated, right? It's the solar wind dominated side of the puzzle that nobody treats. Nobody thinks about it, right? Nobody gives a shit about coronal holes. I was writing papers about chronal holes and really nobody gave a flying toot about them, right? They're just boring. But the thing is, if you looked at the sun with Doppler vision like a shark, the only thing you would see would be chronal holes. You wouldn't see all the active regions. You'd just see these huge big things coming tearing right out at you, right? So be like in the 90s watching a 3D movie. Well, show my age. But the problem here is you've got this thing where you've got two bands of activity in the ascending phase, and in the descending phase, you've got four. So you've got this crazy systematic change in the atmosphere. And I'll overlay my crazy Hale cycle plot on top of this. So in the ascending phase, you only have two bands at mid-latitude. And as you get past solar maximum, guess what? The next Hale cycle is starting to interfere. Activity starts to come down, right? So what's the orange part? What's the orange question mark? What are we hunting for next, right? If I draw my average sunspot cycle on here, you can actually see the activity cliff. Sun makes very few spots after the activity cliff. In fact, it makes nothing. It doesn't make, I think it still makes a few C-class flares, but M and X are off the table pretty much. 96% done, dead. It's pretty fascinating. So what you're seeing now is this interaction between these large-scale magnetic bands. They're not just shaping the amplitude, they're actually shaping the cycle itself, right? So there's more to the puzzle of understanding solar activity than just the peak amplitude of a cycle, right? It's about the shape. And the shape seems to be robust, right? It's a repeating unit, whether it's the butterfly diagram you're looking at or the kind of coarse average cycle, the thing wants to repeat itself. I've got all this repetition in here. But just to illustrate, right, you might think I'm completely full of shit, right? Then you're welcome to think that I'm completely full of shit. But let's illustrate with an example. So the top plot here is the F10.7. So the solar radial flux going back, actually the record goes back a lot further than this, but I just picked 1970 as a good date because that's where I've got solar wind data from. So you can see here, all I've done is I've taken a day's worth of data and associated it with a longitude. So for if you scan across this plot, every vertical line in the plot is our full rotation. So I go through time, and you see that at the Cameron point, so those vertical dashed lines, the F10.7 just goes through a cliff, right? Just stops. Bing. The corona, as much as it switches on at the terminator, which you can see, switches off at the Cameron, right? Why? And it's always the same. It's always 0.8 or 0.6, 0.6, 0.6, 0.6, right? It doesn't matter. But if you look at the bottom plot, so this is where I'm going to really jack with your heads. It's the same plot, but now using the solar wind data measured in space, right? So what you're looking for here, red, is persistent high-speed solar wind. So you see the fact that after the Cameron, you see these beautiful inclined streaks of red. Do you see that? They're coming down from the top to the bottom. Those are your chronal holes, right? So you get this beautifully organized pattern of chronal holes that start to come through the solar wind data. And it happens again and again and again and again, right? And so if you now draw your eyes across the bottom file, you can see the difference between the light side and the dark side of activity, and it's just constantly going in and out, right? And there's a little bit of a battleground, right? So we're actually entering the battleground, right? Right now we're in the battleground because now the low latitude chronal holes are going to start to appear. And so you've got this mixture between activity that comes from the active regions and activity that comes from the chronal holes. And so it's going to get really messy, right? For the next couple of years. And that's why the orange question mark is there, right? It's a bit of both. So you've got little bits of cycle 26 and little bits of cycle 25 starting to fuck with one another. So you can put on this also the polar magnetic field strength with time. And this is where I launch into a rant about the polar magnetic field strength and the fact that everybody's always talks about the polar magnetic field strength as actually being the best indicator of the next cycle strength, except this time, right? So all the cycles preceding this one have gone down. Well, we've only been measuring it for 30-something years, 40 years. If you believe that the polar field at solar minimum was an indicator of next cycle strength, cycle 25 would be the same size as cycle 24, but it's not. So I don't know if that dragon is now dead, but we'll see, right? But one thing to know from the polar field strength is, of course, that we've crossed zero. So it looks like that polar reversal has happened. In fact, that was probably all the hoopla from last week, was that, yes, the polar magnetic fields seem to have reversed. So solar maximum was here, right? Okay, great. Awesome. Bang on. We're spot on the money, right? In fact, even our crude average cycle tells you that, the first quarter of 24 was when it happened, right? So no sleight of hand, right? So anyway, what's next? So you've got all these diagnostics at play, right? And so one of the things that was in that 1988 paper, and I really, if you're a historian or a forensic kind of scientist or interested in any of these stuff, I encourage you to go read it, right? There's a guy on there called Dick Ultra, and Dick was not treated fairly, I don't think. And one of the diagnostics he came up with, he actually lived on he worked at Kit Peak, and he kept this data going day in, day out for decades, right? Because he basically derived the pattern that's at the top, right? So this record actually goes back to 1939, but we won't talk about why the Germans were taking measurements of the chrono in 1939, but I think you might be able to guess. And the record's been kept. They've been observing the corona through chronographs since that time. And what these images are in the middle panel here are basically scans around the outer edge of the sun. So the plot I've got in half, it's actually a very thin annulus. And then what they do is they find where the peak intensity is a position of clock angle around the annulus. And the plot that I have in the middle in that horrible color scale is just a map of the maxima, right? So it basically plots the peak brightness as I scan around the clock, right? And so in that, do you see the pattern? So you see the polar reversal surges, you see the stuff that sits at 55 degrees latitude and starts to come down. This was all in the 1988 paper, right? All of it. And of course, we picked it up. We could do the same thing with EIT. So that's the second panel. And then you can do the same thing with the stereo spacecraft. In fact, you can see the heliospheric offset in the data if you look at it really carefully. And then the bottom is SDO. And so all of those things can be readily combined. And you get this, right? So you now get this full map, not only of the sunspot number and where it may go in the future, but you also understand that the unit expression of coronal morphology is also going to follow that pattern, right? So what comes next? The polar coronal holes are going to start opening up anytime. And then our buddy at 55 degrees is going to start appearing, right? What is going on at 55 degrees? Well, you get weird shit like this. See in the bottom left-hand corner? You see these really anomalous, weird coronal holes. They have a really kind of looks like a rigid upper latitude edge. In fact, if you squint, you can read the time and go find them for yourself and look at the rotation and the next rotation, then the next rotation, and then the next rotation. And you see that this very distinct edge, you want to guess what latitude the edge is at?
55.
Yep. And of course, when the coronal holes fully form, what is the lowest latitude of the coronal hole? You can see it in the plot, 55 degrees. So once the polar coronal hole forms, it doesn't come, sure, there's excursions that come below 55 degrees, but on average, it doesn't. It just sits there. Boo boo. So there's something weird going on at 55 degrees. Maybe we should figure that shit out. Right?
Yeah, apparently.
So anyway, people ask questions now. Okay, so smart ass. Now that you can do this, what can you tell us about next decade? They said, well, we saw this beautiful story about the L5 Vigil mission, right? Vigil is this, they're going to fly a magnetograph out behind us so that they can see around the limb of the sun. So what's the limb to us will be almost this center to them. And so the idea is you get an early warning system for CMEs, right? That's in principle what you're going to do. And so I thought, well, let's see if the launch of this thing is actually going to make any sense, right? Because I'm interested. I want to see if it sees the Terminator because I'm going to look for the timing between things happening in L5 and things happening. I'm really perverse about trying to figure out how quickly the switch flips, right? Because actually the amount of time it takes for the switch to flip at the Terminator tells you a lot about what's going on inside the star, right? So if it's our best estimate is 28 days. What if it's 5? And what if you can track it actually rumbling around the atmosphere? We think it's there from the last one, but you haven't really dug down into that. So anyway, it turns out that if you're going to launch Vigil, you're actually not doing it at a bad time, right? So they're going to launch in 2028, so they will miss the cliff. They will cruise out to L5 and be on station right about the time that the next Terminator is going to happen. So it'll be right on time for boom time in cycle 26. So that was lucky. Because sure as fuck it wasn't planned. So anyway, are we going to win the World Cup? Nah, probably not. Doesn't matter. It's a lot of fun. We have a model of Sunspot Cycle 25 based on a even crazier model, but it seems to be working, right? So it's been tested in real time and in public, right? So you're welcome. Solar maximum is here, but it's only one part of shape, right? The shape was I yell to my kids when they're playing soccer, shape, right? Like people that are not soccer coaches won't understand what that is. But you spend 3 years coaching 7-year-olds that there's actually a formation to play in the game and it's not just all hovering around the ball, right? So the next validation point of the model is the cliff, right? There's other things that are going to happen, like the things like seeing these high latitude coronal holes that slowly migrate with time, really slowly migrate with time, but really slowly. Are also validation points. But like I said, you can cut this out, but nobody gives a fuck about coronal holes, right? Generally speaking, they're just dark things, right? But the next step is the cliff. But like I said, the Hale cycle that carries cycle 26, we're going to be able to validate that that's there sometime in the next 6 months. Who's crazy, right?
Yeah.
We got the last one right, but nobody seems to give a shit about that, right? I mean, we wrote a paper. It took about a year and a half to get through the peer review, but it pretty yeah, and it's scurrilous. It's why I'll never publish in the Astrophysical Journal again, right? Never. I'll do that in public. I just said that in public, so never. And yet they published a paper. They published a paper a year later saying that they were the first to find cycle 25, right? Some scandalous shit going on in there, but whatever.
Right.
But we're already at the point where cycle 26 could be forecast. I'm not going to show you, right? But it could be. It's interesting. And just for shits and giggles on the left-hand side here, I've got the 2 updated versions of my animations. And like I said, the red, white, and blue things have not changed, right? Those are all set by the clock. Whatever the clock is, whatever's going on at high latitudes that keeps this thing synchronized, right? The interesting one is the bottom one. So the top one's the spots. You've seen it a bajillion times now. The lower one's the flare record. Remember how I said when it hits the cliff, the flare's just gonna hits the cliff. It's kind of cool. It's kind of mesmerizing. So in this case, I think the yellow points in there are C-class flares, green are M-class flares, and red are X-class flares. You could drive yourself nuts by looking at the red ones and showing that, oh shit, the red ones only occur when there's big surges in the number of sunspots. Holy shit, really? Yeah, because you're now then getting into meteorology, my friends, right? And the fact that that big rotating ball of crap in the sky is actually a meteorological object and not flat, right? But we won't tell the theorists about that. So with that, you managed to survive a shit ton of slides. Congratulations.
We
I
made
think we
it.
were promised like 100 and some, if not more.
I could go back through them. That would be close.
Yeah, I thought there was like a no.
There's a bajillion. So there's your polar chrono holes, right? So where I was looking, I couldn't really see when I was zooming, but there's where you go looking for cycle 26.
Hmm.
And there's where your polar chrono holes are going to appear. Do you want to anybody want to put a bet on? Oh, I see Tamitha's joined. Are you here under
Yeah.
your pseudonym? No, she's quiet too. It's like,
Yep.
Yeah.
uh-oh.
I think
She has
she's
no volume.
I know. I think she's talking, but I can't hear anything.
She's wagging her finger.
Okay.
Hold up, hold up.
Hold up. All that technology. Look at it.
Yeah.
It's just a green screen background. It's not real. Promise.
Now,
Hey, there we go.
What's that?
we got a sound now? Okay, good. Yeah, I just got too many mics set up, so I'm running off a different one. No, I completely forgot, but I was here the whole time, so
Yeah.
Oh, really? You're just skulking around in the background?
yeah, didn't want to, steal your thunder or anything like that, so I was just kind of sitting back smiling. Yeah, the problem I have though, Scott, is that I've got 2 of my ex-students here, or actually one is a current student, one is a former student. And you're saying Hale cycle, and you're saying it without saying, you're talking about the 11-year cycle and you're calling it a Hale cycle. And it's like, okay, come on, help me out here. Don't make me have to explain.
No, I told everyone it was the completely arbitrary magnetic cycle.
Well, yeah, but 22 compared to 11, I talk about the Schwab cycle. So I've got to, I got to make sure that they know the difference and matters
Yeah,
to
I approximately covered that in slide 5 of 60 something.
Okay.
Right? But yeah, no, but I always thought it was just, oh, it's half. That's interesting.
Yeah.
But you never hear any discussion about the Hale cycle in any textbook you find, right?
No.
Far less the fact that you can actually fucking observe it. Right?
Yeah.
Well, again, it's the same reason why we have Enlil having, the M in MHD is that magical like outline of an M. It's not a real M,
right.
Magnetic field is what do we need that for?
Yeah,
only
I used to
The most
I used to
important part of the whole thing.
I used to joke it goes between a mu and a capital M, and it depends on the situation.
Yeah, I can see it.
So, yeah, no, we don't worry about magnetic fields in this game.
Right, of course not.
Obviously relevant.
One of the big questions I have, Scott, regarding, of course, you're talking to a crowd that loves corona holes because
Yeah, we actually do like corona holes.
they know.
Oh, you're my kind of people then.
Well, that's the only time when you're talking to Aurora photographers, that's the only time that you can actually plan 27 days in advance to see Aurora. So
Yeah.
that's one of the most fun parts of the cycle. But the
Yep.
thing that I'm curious about is when we get into the meteorology side of things, I would like to see whether or not it's going to be one of the best places to study pure meteorology when you see sunspots emerging in the center of a coronal hole. Like there's nothing going on. Suddenly you see these things, and they only happen when you get those big trans-equatorial coronal holes and you see these sunspots, these massive sunspots just emerge right through them as if they weren't even there. And I find that fascinating.
Anemones?
Hmm?
What do they call those, anemones?
I don't.
There's a name for them. I've got to go look that. I used to know, but yeah,
know.
you've got a coronal hole and you get the dipole pops up in the middle of it and it's pristine.
Right, and it's pristine. Why doesn't anyone ever study those? I mean, you know the name of it. I didn't even know that there was even a name for it because I'm not
I think they're called anemones.
Who studies them?
Crazy people.
No.
I mean, I no, honestly, it's kind of like you can find. So if you search for an enemy, you'll find them.
Like see an enemy? I mean, how do you spell this?
You'll find them, right?
Okay.
But it's kind of like through the solar physics literature, they're like the papers on the Bastille Day flare, right? People look at them in isolation, but not as part. It's kind of like modern medicine, right? You don't really look at this underlying condition, just the symptoms.
You're just looking at that case. Yeah, it's a one-off.
They treat them in isolation. It's like, I'm going to write a paper about this filament.
Right.
Sorry. Boring.
10,000 other, but I had never seen ones where people would actually study them at all. I mean, unless they're trying to look at, obviously the neutral line and inversions or rotation or polarity.
There's a lot of morphological things, but then they don't look at morphological things. They look at this one-off, right? My PhD advisor told me never to read a paper with a title and with a date in the title. Never.
Interesting.
Because it's not focused on the big picture. It's only focused on that one specific thing that could be irrelevant. So he's like, cut your workload down. Only look at the other half.
Right. Well, that's also the part that nobody else is looking at.
Yeah.
Because the low-hanging fruit, you know what the low-hanging fruit is. It's always doing one-offs and saying, well, I'm building up statistics for an analysis later.
Yeah, I've never been a good one at looking under the lamppost for my keys.
Right.
So, which is why I lost my keys 6 months ago.
Yeah, but people have built, people have built entire empires that way.
Yeah, no shit. So
I'm taking notes on that. I'm just curious about studies that have been done in that, because I just wonder if you were to ease a meteorologist or schmooze them into, seduce them into actually doing analyses on the sun for looking for weather patterns, looking for Rossby waves, looking at Hadley cells, as we talked about, and so did Lindsay in my class the other day. What part of the sun, what part of the cycle would you want them to look at first?
Well, but I think we need to take right. So fortunately, from 2010 to 2014, we have meteorological data for the sun, right? So we actually have 360-degree coverage. And so that's a totally rare data set. The problem with that data set, of course, there's no magnetic fields for it, right? It's only images. And so I've always said that if we had magnetograms on the two stereo spacecraft, none of this would be a discussion at this point, right? So it'd be like the equivalent to watching a hurricane form off the west coast of Africa, right? You'd be sitting and you just sit there and like your GOES satellite observing the sun, and you'd just be watching this magnetic field just billowing out, right? Cyclogenesis or whatever they call it, and the phenomenology would be the same. So I mean, for me, there's a reason why I've kept that data set. I built that data set and kept it. It's in a pristine place on my hard disk here. It's a truly fascinating. You just put those movies on and you're blown away by the just the connectivity, because you can freeze it at any longitude you want and just sit at one longitude and watch it evolve over 4 years,
Yeah,
right?
but you don't get the latitude, so you know that.
No, well, I mean, so that's the trick, but it's just a different. So you start to see these Rossby pulses coming
Mhm.
through the data that you don't get appreciation for because you think the sun's flat, right?
Mm.
So this mad rotating thing. So yeah, no, uh, if you wanted to get them looking at data that would inspire them, you could even color code this data so it looks like the ocean, right?
Right, right.
Here, my buddy's back again.
It's all good.
But
Hey,
would
I'll
you
be up
want,
in a sec. He
would you
wants
want them?
he wants a game.
Of course.
Right, go away. All right.
Would you want the meteorologists though to look, to look at the multipolar sun when the dipolar
No,
is just,
when it's really complex and nasty, I would think that probably the most pristine, simple state is the ascending phase, right?
yeah,
Because you've only got two bands per hemisphere. The flux emergence is relatively clean because the connection between 40 degrees or 35 degrees latitude in the north and south is 70 degrees. So the connection across the equator is actually smaller.
okay,
I think when you get into the declining phase, and as we're about to see, you're going to have something at 50 degrees, something at 25 degrees, 25 degrees. It's going to be really complex,
right,
right? So you see this as you said, octopolar almost kind of chronal configuration. So that's what that Ultrox map is showing here, is like it going from dipolar to quadrupolar to octopolar, right? It's
right,
really wet.
right.
I've always wanted to try and take this data and actually reanimate it, like back it back out in a pristine world. I should set myself that challenge. Do you know what I mean?
Just
So you could take one of these scans and actually reconstruct what the coronal shape looks like.
map it out I mean, we do this all the time for Earth in the magnetosphere. They'll take particle distributions that they've gotten from orbits, even in the equator, and then they'll just map it in a spherical coordinate system, in a dipolar coordinate system, to create radiation belts so that you can see the bouncing of the particles. And it's granted, it's not, you don't really know what's going on at the poles, so it's an isotropic distribution along those L shells. But you could do the same thing in spherical coordinates, in spherical harmonics. I mean,
Right.
don't ask me to run the math for that, because that would give me a headache and I really don't feel like doing it. But that's a great project for, a mathematically inclined graduate student to turn around and take something that's reasonably isotropic and say, okay, now just assume it's isotropic and now
Assume a
map
spherical
that.
cow.
Yeah. And assume spherical symmetry. Okay, grand, fine. The next step, of course, would be to look at potential source fields, mappings. But just the simplest would be to just use spherical harmonics.
Yeah, no, I could probably remap it. I'm just lazy.
Well, that's not lazy. That's just looking at that. And that's a pain in the ass to try to do. But someone who loves math, there's
Yeah.
No,
there's
Not me.
probably a Python like routine for that, for goodness sake.
there's probably some MRI reconstruction thing that could be used.
Ask ChatGPT.
I probably will. Shh, it's a secret.
Yeah.
But it would be really cool. It'd be an amazing way to visualize it if you could do
Yeah,
that.
I mean, one thing's to visualize it. I mean, it's another way of validating. It's kind of like you show the butterfly that is like this guy. I love this, right? You show the average butterfly. Hold on, I'm making everyone sick.
That one,
It's
I
okay.
like
Right?
that.
So you show the statistical average of the butterfly against what's actually happening, right? You could do that with chronal morphology too,
Yeah.
right? Just play this thing in the background. Oh, look, you expect this to line up. Look, what? It's lining up. Damn it. Like, wow, we don't. But part of the problem, it kind of goes back to the initial discussion about the kraken, right?
I like the
You're
crack.
You're
now-
only using the tentacles to infer what's underneath. But when you're looking at the sunspot number and you're looking at the butterfly diagram, you're selecting only a subset of the tentacles, right? And if you worry about this stuff in the context of, like I said, about inverse problems, you're making the range of possible solutions massive, right? So as you add more and more data, the range of possible solutions in principle comes down, right?
In principle.
In principle. And so this, what we've talked about for the last 15 hours here is one possible outcome, right? And who's to know if this is just a fluke, if it works for right now, or if it's worked for the last 400 years? You know, when I talk to people about why are we not using more data, why are we not constraining our models of the solar dynamo, presuming it is a dynamo, why are we not using more observations on it? Well, the sunspot record's 400 years old. When you can come up with something that's that long, you can let us know as well. I think we could probably train AI to replicate what the extended cycle looked like back to the 1600s.
So what was the pushback when you asked that question of your peers?
I said, you're fucking mental.
Why? Because this is the way we've always done it?
Probably. That would be a approximately good answer. I think I was told that I should go play with myself.
Go figure.
Yeah, I think that
Not a visual that I want to see right now. No, let me scrub that from my head.
but I think the principle there was that it's until you've got something that can really help as constraints. So the spatial patterns are not something they can do, right? Because they barely get the butterfly diagram.
Right, right.
And so, you know, but that's part of what we're trying to emphasize is this is more than just a peak. Right. It's about a shape. You're capturing evolution now. It's not just the sun is replicating itself on a time scale of 22 years. Right. And the time, as someone told Bob last week, time is squishy in your model. It's like, yes, it's squishy. Right. Has to be squishy.
Well, but here's something that I find very fascinating is that you have time as, you know, because it's a periodic thing. It's far more constrainable, and that's one of the things that you have above, for example, some of the stuff that we do in again, I hate to go back to Earth for a second, but to talk about some of the models that we have with particle distributions. There has been, for those who are very familiar with the AE8 and AP8 model and the difference between that and the latest, which is AEP9, what they tried to do in that model for basically radiation dose and particle distributions in the Earth's radiation belts and basically anywhere inside that system is they tried to make a global assimilative model. So you take all these different data sets in all these different orbits and you basically create a global distribution with them. And what we learned very, very quickly, and I can say this now that I don't work at aerospace, but what was found very, very quickly is that the damn thing doesn't work. Basically, everything diverges and you blow up. You get error bars that are larger than the mean.
Oh, but then you have to invoke the magic of data assimilation.
Yeah, right. But it becomes unphysical. And the problem is that people still try to hold on to it. And they kept thinking that, well, the more data sets we add, the more that is going to make error bars shrink. And that is a real fallacy. And
it has to be the right data.
It also, the problem that we have is instrumentation. They forget the instrumentation errors and the intercalibration of the data. First of all, the different epochs, totally different constraint, totally different variables, even in the Earth's magnetic system, right? Even the magnetosphere itself was changing. So you have all of these different assumptions that you make that in theory would end up making the data better constrained. But I will admit that I do worry about that a little bit here with the kind of data, just taking all this different data from all these different epochs and all these different instruments, even though it's remote sensing and you're looking more qualitatively as to whether there's a bright point or not and where it is. I do worry about errors like that. But the neat thing you have is periodicity, which is something that we don't have really in the magnetosphere. Not like that.
Well, and that's the thing here. I don't think so. I was pretty gobsmacked when we went back. So we found a paper from 1833, right?
Whoa, really?
Which catalogued, yeah, was it? It was cataloging the first 3 decades of observations from the Archetre telescope. Was it 66 or 33? I can't remember. And they basically saw the extended solar cycle pattern in those first 3 decades, right?
Really?
That's pretty cool.
Yeah, I can find you the paper. If you can read Italian, you'll do a great job with it. Probably can get it AI at this point, but it's fascinating. And then there's Norman Lockyer's son published a paper in the early 1900s, refinding this from the observations at Kew Garden. So they were plotting the latitudinal progression of prominences.
Huh.
Right? It's beautiful.
Yeah.
Right? So I went back and I found the freaking record. Right? And so I went back and digitized the record. And I was just kind of, because what I was looking for was the time capsule to go back, right? How far back can I go?
How far back can you get?
And it goes back to the dawn of H alpha photography, which is in the it's 1860s. So I've got to look and see when that Italian paper is, but it's not long. It may be 1893. It's a long time ago.
Weren't you kind of forced to do that because of the referees? Because people, they got you kind of pissed off because they're like, you weren't showing them enough statistics or something like that?
I got really pissed off because they said, well, 4 of these is just you're cherry picking the data, right? So I found 14 and stuck it right up them, right? But this is so see those red dots at the start of the sequence here? Those are from Archetre because they only reported them annually, right? Okay. So they basically made a distribution of the filaments on the disk annually. So they have a PDF of the number of filaments. They see them as a function of latitude.
I can't believe they actually measured them.
They did it. Right. I know, it's absolutely beautiful.
Totally.
But it's made possible from, so they had Balmer alpha photographs, plates. You can still go to the observatory and see the frickin' plates.
So this is, so Tanya brings up the solar activity in the year 1966 from the optical and radio observations obtained at the Tree State Astronomical Observatory. That's the paper she mentioned.
Yep.
That's pretty cool.
Very cool.
Isn't it bonkers? Right?
Yeah.
Nice.
So they basically found this 100 years before Wilson did.
Well, the sun's been pretty periodic. And this is and it's really good for all the doomsdayers who say that the sun is, doing all these wacky things, and we're going through the galactic current sheet, and the sun's gonna, go micronova. It's like
it's not as bad.
The sun's doing normal what it's done for the last, at least several hundred years.
Not as random as you think it might be. It's like when you smack people in the face for saying, yeah, flares aren't random. They go, whoa. Well, they're meteorological things.
What I'd really like to know is, as we go through these different Schwab cycles, right? These different 11-year cycles, as we go through them and we look at the difference between the A greater than 0 cycle and the A less than 0 cycle, and why ascending phases are bigger than descending phases on certain cycles.
Oh, where's Bob?
Oh, yeah.
You know the sun knows which way is up, right?
Yeah, it knows which way is up relative to the intergalactics, the magnetic field of the intergalactics.
The sun knows which way is up.
Yeah.
Right. It's weird, right? Because that's one of the things that so I showed here. Hold on. I haven't got it in any of my slides, but you can make a circular clock of this thing, right? Because you can the Hilbert transform allows you to express it as a position on a clock from 0 to 2 pi, right?
Right.
So you can remap time into a circle. Your brain melting yet? You can either do the Terminator to Terminator cycle, which I've done here, or you can do the Hale cycle. So it's two Terminators, right? So
Right.
it's a full 22 years.
Have you done that 22 years in
Yeah,
your,
we've done
papers?
that.
I,
Yeah,
you don't recall that. I remember the 11 year, but I don't remember
we've
the
done that, and you can see distinct differences between the odd and even cycles,
That is
right?
pretty.
So the magnetic configuration actually has a role to play in things that you wouldn't necessarily think it would give a shit about,
It
right?
has to be coupling to the intergalactic field, doesn't it?
Well, that's where the cosmic ray flux gets wanky, right?
Of
So
course. Yeah. Hey, careful. Tanya doesn't know that yet. I've been teaching her.
All this a primordial field. Hi guys.
like now, like everybody's chiming in. Team Linker's chiming in at this.
Yeah, you got this.
Now you're going down the rabbit hole of any one of our meetings.
I like it. I
All
dig.
right, shut up.
Well, were you going to talk about the Hale cycle clock?
Sure, although I don't have any plots on this machine, but as you said, yes, if you do it as a 22-year clock, you can see a difference between the top half and the bottom half.
Yeah, no, it's bonkers, right? So yeah, it's interesting. So it's kind of like these tertiary insights you get, right? So the first one's the sunspot cycle, and then you get into the secondary stuff, which is the shape. And now you're starting to worry about tertiary and quaternary stuff, where you get into crazy shit like grand minima. And
Right.
why the fuck is cycle 2024 weak? And why is 20 weak? And where the hell was cycle 4?
And we need to, and another thing we need to look at are things like energetic neutral atoms and watching as they come in through the termination shock and how they get frozen from the location they came in, because it's different. It's showing something about the shape and the orientation of the intergalactic cosmic field. And it's really kind of cool if we can lock all that stuff together. But
Maybe the fifth order thing might be that it's not isotropic.
well,
Shit. Oh, how many of my fundamental premises just fell apart because it's not isotropic? Oh, fuck.
Well,
Well, it is. We have to start with a spherical cow.
yeah.
So I actually have a very, I know you guys are probably desperate to be done with us, but there is actually a version of this slide where underneath it is a spherical cow.
okay.
Right? So the kraken starts as a spherical cow. So don't be alarmed.
I won't.
Well,
I
you have to.
promise.
You have to. You have to start somewhere and build up.
So anyway, I like the kraken. You can't take it away from me.
I won't. I like it
Put a
too.
little thought bubble that says "moo," so it's
Yeah.
everybody knows it's a spherical cow.
I could go find it, but I won't.
Too funny.
Any other? I haven't been checking any of the questions. I've just been rambling.
No, we've been getting to them. So, but yeah, no, this has been fun. I like listening to you guys talk because I mean, I'm probably the least most scientifically inclined here. But it's super fascinating. It really is. I like trying to learn more about this stuff. And I have through all you guys, so this has been awesome.
Yeah, we're a resource for you. So, doesn't mean we can answer everything. And usually if we do try to answer, we're full of shit. So
That's okay.
we appreciate what you bring to the conversation. I'm always gobsmacked by some of the pictures that you post. So
Yeah, I'm just a photographer that really loves this stuff and I try my best to understand it and I get bits and pieces.
there's no such thing as just, right? So, but yeah, like
That's what I'm saying.
yeah, right. Totally true. Somebody telling you a bit on the 55 degrees thing. The answer is don't know.
Yeah. That is pretty
Actually,
cool.
we think it's geometry. But
Okay.
does that get too much into celestial design at that point? We think it's all about the internal geometry of the star. Right, why it's 55 degrees. It's kind of like our the Arctic Circle kind of deal, right? The Hadley, it's getting into what Tamitha was talking about Hadley cells.
Mhm.
Right? The cellular, there's a polar cell and there's cylindrical flows around that. So who knows? Maybe in 5 years when solar orbiter gets up high enough, they'll rediscover the fact that 55 degrees is important.
Not with, come on, their inclination's only gonna take them to what, 35 degrees at most?
Yeah,
You
but
think high enough?
I know that crew. They're going to try and say that they're the first to discover that there's an uncharted territory at the North Pole. So
Never studied.
Wouldn't it be cool if they found some like hexagonal wind?
I think an obelisk would be really
That would be
spectacular.
really cool.
Yes.
And then everybody, suddenly there'd be these massive missions to like Saturn and Jupiter. There'd be these
Right.
massive missions like crazy. They'd all be polar orbiters of those.
Like Interstellar.
Yeah.
No, I think that I think they'll get a hint at it. They're going at the right time. They'll see something odd at 55 degrees, and I'm hopeful that it will motivate further studies because
Yeah.
I think that's the source of the Nile is right there. We have an idea, the dynamo is not happening at mid latitudes; it's happening at high latitudes.
We need a Ulysses imager.
Oh, they descoped that one in 1980, what something?
Yeah, Ulysses. Oh God, it was gorgeous.
So you know that Ulysses was meant to have an observational counterpart.
Really?
Yeah, but it was
Yeah,
too hard
it was
to
going to
find.
launch. It was going to launch on the space shuttle, and it got descoped by the Reagan administration for
Yeah.
I can't in favor of something else. I can't remember. Bob will know. Bob's the fountain of all wisdom.
I'm not sure it got. I thought it was the Europeans were going to provide it.
Yeah, I can't remember. There's a story that the Ulysses was going to have a sister.
Prometheus.
Well, I do know
I
that,
guess his brother.
right, we
Yeah.
had the plasma analyzers and stuff that ended up flying on what, oh goodness, what was it? They were off the shelf. They were COTS off the shelf because they were stored from Ulysses. There were ones that weren't used. So maybe they were extras from the mission that were ready to go for Prometheus.
Think about how much the field would have advanced
Oh God. I mean,
if you had things flying over the poles 20 years ago.
It
Yeah.
revolutionized our understanding of the
Ability.
solar wind. So I can't imagine it wouldn't have done the same for our understanding of our star.
No, so when at some point you guys, I'll send you some of the movies that you can construct from the stereo and SDO and the polar projections that you make.
Oh.
You see these beautiful spirals, right? And you can see the rush to the poles and how it's a big spiral arm that forms and then it just disappears. Then the polar coronal hole reforms. It was just
Cool.
Yeah, that's cool.
it's absolutely a mind fuck, right? It's like I've always wanted to put it on like 4K, put some trance music to it, and just play it on the biggest screen I can find.
That sounds like a good
And
time.
then you can blend it with the coronal ones and start to see how the coronal holes form and fade and disappear, and how more than half of them have no relationship to active regions at all.
Right. Right.
It's completely baffling and not in the textbooks also. So
And we're seeing some of that already beginning. As you were saying that right now is the real war zone. Well, it's already starting, because if you look at the sun right now, we've got two near equatorial coronal holes, and right in between there, sandwiched in between is an active region. So
Yeah.
we're already seeing it.
yeah, the
And
war.
it's just going to make the next few years just hell until we get the big nice big holes. I can't wait for those.
Wars, the big organized ones where you get those high-speed steady streams from.
Yeah.
Right, persistent
Yeah.
ones. Yeah.
Yeah. No,
Those are going
it's
to be,
cool.
and we're going to see fast solar wind from those. That's faster than we've seen at least 2 solar cycles. Well, I would not be surprised if we saw 800 kilometer a second fast solar wind streams again. We haven't seen that
You heard
for
that?
solar cycles.
You heard that here, folks.
Yeah.
Observe-
Yeah.
no.
Oh,
And
Cycle
again,
spoils.
Tanya, that's not the Tanya, that's not the one. Hold on, I'm going to find you the right one. Hold on.
Uh-oh.
I keep talking.
Okay.
Well,
Talk amongst yourselves.
and Scott, what I was, and Bob, both of you, what I haven't heard from you either is that, you talk about the sunspot cycle, the sunspot number being stronger, everything being stronger, the magnetic field strength being stronger. But when we get these stronger solar cycles, these coronal holes, the fast wind is also faster.
I can't wait to see that. But it makes a lot of sense because it's just better energized, right?
Already seen it. Yep, already seen it. So that
Mm.
should tell you something, that deeper down in the convection zone, wherever all this stuff is happening, what's going on under there is generating faster solar wind, more energetic, particles being pushed out.
Where are you?
Well, I'll welcome that. Can't wait.
Yeah, we haven't had stuff like this since I've said it multiple times when I've looked at the shape of the magnetic clouds that we see and the strength of them and the speed of them. And when we get fast solar wind, even from these small pockets of, these small coronal holes, I keep saying to myself over and over again, we haven't seen this kind of stuff since cycle 22. This is the stuff, these are the types of events that I saw when I was a grad student and what I studied, because I was studying cycle 22 quite a bit, 21 and 22.
Mhm. Yeah, so it's good. Yeah, so basically cycle 24 is like the anomaly, it seems like now.
It is.
It is.
It's exactly the opposite of what the public and pretty much all the operational folks want to believe, because their memories are so damn short.
Yeah.
You I remember people talking about the unusual solar minimum of 2009.
I remember Tom Huxtable going, it still hasn't dropped. It's still there. We're 2 years out. He's saying this in 2004 or 2006. He's like, we're 2 years out from solar minimum. And it's like, we were supposed to be there already. I remember him at like Shine, or I think it was Shine meeting. He was just losing it. Going, we've never seen this before. We have no idea what's going on.
Oh, it threw people for a loop when you had the TI drop of what they thought was the threshold.
Uh-oh.
And that spewed out a whole bunch of papers. Hold on, I'm slowly getting there. Believe me, I'm actually doing something here. I
Okay.
promise.
Yeah, we can tell your internet. You must be searching on the internet and downloading stuff because you're pixelating.
Yeah, he went fuzzy.
Oh, that's my brain.
That's my brain after all this. I'm
All
like, oh, I
right, so
gotta put all this together.
here's the paper. Hold on.
Cool.
So it's actually from 1933. Hold on. I'll switch over in a
And
second.
Wilson's paper I saw was it looks like a letter in Nature, but it wasn't. It was very short.
Yeah, but it's part of a epic series of papers.
Okay. So you had said something about Wilson, some of Wilson's other work, but it was definitely wasn't in the Nature paper.
So this is from 1933.
Oh wow.
So it documents the first 60 years of observations from Marchetri. So it's migration zones of prominences over cycles.
Pretty cool.
And it's epic. It's really such a beautiful piece of work. So anyway, it's real.
Well, thanks for that.
Yeah, if you can read Italian, Italians, yeah,
Cool.
it's pretty cool.
Right on.
All
Okay,
right.
I will.
Yes. I
I
figured
gotta hang out with my husband a bit and take
Yeah.
care of my daughter for school tomorrow. So
well, we're glad
Thank
that
you.
came here.
thank you
Thanks for popping on.
And Scott and Bob, I need to ask. It is time for me to update some of my materials in my SWEN course. That I have some of you guys' materials, but it's probably dated from like 2021, 2022.
Yeah.
So I'm wondering if I can grab, Scott, I still have your charts from Italy. So I'm wondering if I can, with your permission, with you guys' permission,
Sure, steal what you want.
Some of that
I mean,
stuff.
borrow it. Yeah.
Yeah.
But hey, I'm training meteorologists in your work, even
Yeah,
married that.
you're welcome to steal whatever you want. And if you need more updated stuff than that, I can happily give it to you.
Cool. Yeah, but
But Bob should give you, if you want to toy with them, you show them the Hale cycle clock.
Uh,
So the 22-year clock is a the Hale cycle clock is a Kubrick-esque type move.
Cool.
So
Uh-oh.
uh-oh. See,
yeah,
now we're going there.
that's the tilt, and you can see 8, 9, 10 is doing weird things. You can also see the difference between odd and even cycles as to how fast they drop, even if you account for
Yeah, wow.
that. I don't have.
I'm trying to think if I even have any of those floating around somewhere.
Wow.
But yeah, no, so that like this idea of so when you look at the red, white, and blue, we call them bandagrams because we can't think of anything better. But the kind of cartoon representation of the Hale cycle.
Mhm.
So what that basically means is that when it's oriented blue, red, blue, red is different from when it's oriented red, blue, red, blue. Right? So the just even the change in the magnetic configuration produces these kind of third order changes, which if you're in a kind of really subtle environment, right, like space, they can impact, they can bite you in the ass, right? So it's not really the first order things you're worried about. It might be the fourth order things you're worried about,
Right.
And so it's really subtle, but it's really the thing to me with all this shit and boring everyone to tears is that it looks elegant. It's like it boils, the soup really boils down, right? And you're thinking, oh wow, that looks really simple. You got all this complexity and nastiness at short timescales, and then it boils down to something that appears to be cyclic and repeatable, and it's kind of cool, right? But anyway, whatever. I don't care.
It's it is. It's wonderful. And that's how you know it's real too.
Yeah.
It all boils down to something simple that's repeatable. I mean, that's one of the reasons why your papers, were the most cited for several years, even though they were the most controversial. You couldn't find people, you can't knock it down. You can't refute it. You can say, oh, you're off your rocker, you're crazy. But then when you ask, okay, well, what supports that? What is your argument that supports that? They don't have one.
Yeah. But yeah, it's almost interesting. I was watching anyone watched Ancient Apocalypse on Netflix?
Mm-hmm.
I want to admit to it. Right. So Graham Hancock has got this documentary talking about, whether or not there's a prehistory to the human race, right? That if it goes back further than the last ice age. It's interesting. It's totally, it presents a lot of observational data to support the fact that there was not a master civilization, but there's more organization than you might. It's not just cavemen and Ice Age the movie, right?
Right.
Yeah.
Well, the mechanism, there's all sorts of evidence of things like that where technology existed that shouldn't have existed for these people.
Ancient technologies, and I kind of feel like we should do a documentary about this shit too at some point, except for the fact that nobody would watch it. So you do solar archaeoastronomy. There you go. That's boring.
For some people, maybe. I don't know. I'd be okay with
How
it.
you couch it. I think it's how you couch it.
Yeah.
No, I'm totally convinced it'll be boring. But I feel
found
like I should resonate with the poor bastard.
Ah, here we go.
Cool.
Uh-oh, it's a Hale cycle clock.
it's
Oh,
the
that's
hit,
cool.
it's the 22, yeah. So it's, I think it's F10.7 and the cosmic ray flux. You can see the difference between the odd cycle top right
Mhm.
and the even cycle bottom left.
Yeah,
But,
it blows my mind that photons care about the orientation of the magnetic field, right?
Yeah.
But photons shouldn't give a flying shit about the orientation of the magnetic field.
Yeah, but the photons, when the
how,
photons
how do those
are
photons get generated?
exactly,
Well, that's the thing.
that's it. That's
No,
exactly right.
but you would think they get generated in the same way regardless of the polarity of the magnetic field.
A random walk isn't random when it's magnetized.
Yeah, well, I just think it's staggering that you get this weird odd even partner.
Oh, you're going to stagger home drunk from the pub. You're going to you are. It's not random. You're eventually going to end up at your front door.
Photons shouldn't give a shit.
They're not going to knock on anyone's door. 3 o'clock in the morning.
But it's also beautiful, right? So you've got this what looks like a completely random data set is not random, right? There is a pattern there, and you need to look at it at this scale. So I mean, this is the work that Bob's been really focused on, is that some of these things you really need to look at this scale, and we don't really have a long enough observational record, right? Because now you're looking at Hale cycles, right? So you're not just doing an 11-year. This is the 22-year guy, and the solar wind data only goes back 50 years, 60 years. The F10.7 goes back to the 40s, right? The filament record goes back to the 1860s, and then pretty soon you're stuck with fucking sunspots.
Yeah, that's right. And even less than that before
Yeah.
too long. Oral
So-
record, you know.
But you
Some
can start
huge
start to play games based on this stuff, right? So that's like kind of an insight into the rabbit holes that we go down.
That's cool.
Start to mess with this stuff. So, what will cycle 26 look like?
Well, you already know. Don't give me that. You guys know.
Yes, you know.
That's not the point. If you want to know what cycle 26 looks like, we can send you an email address where you can send money.
Yeah, buy it.
Yeah, like how much? How bad do you want to know?
Yeah.
All in the next 15 minutes.
Yeah. It's a telethon.
That's funny.
All right, guys. And on that note, I will say
Yes.
thank you. This has
Yeah,
been great.
we've degenerated.
Enjoyed hanging out with you guys.
Yeah, thanks for joining in, guys. Good to see you. Mary Beth, Christian, thanks for the invitation.
Absolutely.
Absolutely. Thanks to all of you for coming. That was awesome.
Yes. So this was a great discussion. Like I said, it's yeah, I don't know. It's an honor just to have you guys here.
Just to be in the room. Really.
I learn a lot and I appreciate all of it. So
Finding the ground floor of the research and where it's all happening and where we get
Yeah.
our new take on solar cycle.
yeah, it's really cool. It's neat to be a part of too, because like you were saying, a lot of this stuff isn't even like textbooks or anything. It's all kind of just,
It's
new.
ongoing research.
Yeah, so
Yeah.
it's really fun and fascinating.
Controversial at that.
Yeah.
And
Well-
Scott, this is exactly what I was talking about when I said to give you the floor to rant as much as you needed to. This you absolutely delivered. So thank you.
No,
Yeah.
my pleasure. And you know that this is only partly joking that we're testing this while we're flying it, right? So I think that turned out to be a pretty good experiment to do it just out in the open, right?
Yeah.
So,
Yeah, just like you said, like in real time and just testing it, and it's really fun. It's been fun to watch.
Yeah.
that means we get to I'm pretty confident we're going to get it down within less than 6 months next time.
Yeah.
So, but I want to see some shit blow up in the declining phase so that we can be wrong.
Right. Yeah.
Yeah, I
That's
want to
awesome.
see the impact of some huge explosions so that things slow down again.
Yeah.
So then we get another 24.
We know what we're looking for this time, right? So you imagine being able to call that one.
Hmm.
right? Because everybody, you know what everybody's going to do next time? They're going to say it's average,
Right.
Yep.
Yeah.
right? They're going to say average. I'm saying that on YouTube right now. They're going
Yeah.
to say average.
Still
Average.
gotta find it first.
And I'd love to see some explosions and go, ah, boy, were you. So anyway, thank you guys. I really appreciate
you.
it. Thanks, Bob.
Thank you.
Tamitha.
Yeah, Bob, thanks for jumping in too. Appreciate
Yeah.
all your work on Twitter.
We have lots of papers and stuff to read now, so I'm super excited.
We'll start with the Italian one.
Yeah, I definitely want to do that
We'll
one.
get a Google Translate going.
If nothing else, look at the pictures and you go, holy shit.
Like, wow,
It's
look
the
at
same
that.
thing.
It's the same stuff.
Thought.
Anyway, thanks, guys.
Yes, thank you very much. So I will end
Thank you
this.
both.
Yeah.